Welcome back to Codex. Today's speaker is Eric Weber from Iowa State University. Professor Weber is an expert in frames, harmonic analysis, data science, and more. Today, he'll show us the beauty of the Kaczmarz algorithm. Take it away, Eric.
Thanks, John, and to the rest of the Codex seminar organizers for the invitation. So I'll admit I feel a little bit nervous because I feel like I'm out of practice. Many of you know I'm department chair, and so those duties take up a lot of my time and energy. So hopefully this goes well. I have a couple of mathematicians that I've really looked up to when I think about giving good talks. Well, Larry's in the room, so I'll mention Larry, my advisor, Larry. Always gave excellent mathematics talks. One of them was Guido Weiss, and many of you in the audience actually knew Guido. He would say that if you have a central nervous system, you'll understand this talk. So that is my first objective. And another one was Dick Caddison. And I once saw a talk by Dick Caddison. It was an hour-long talk, and he used 2 slides. He had a title slide, and then he had a slide with a reference with the title of a paper he had just written with one of his students. So Chad's my former student. He knows that I've often recommended less is more when it comes to slides. And so my objective here is to give hopefully a talk that is understandable and enjoyable with very few slides. So here we go. I'll say first that, as you can see on the screen, I've been privileged to have been sponsored by multiple organizations, funding agencies, most of which have had some relationship to my fascination with the Kaczmarz algorithm. And that really is what it is. It's a fascination, and I'm hoping to share some of that fascination with you today. So I'll thank the sponsors. Now I need to, there we go. And I really want to thank my collaborators. So this has been a project that has been 10 years in the making, involving a lot of people. So Palle Jorgensen also is in attendance here. So we've collaborated on this for a very long time. A now retired faculty member in my department, Fritz Keinert, former faculty member here at Iowa State in the electrical engineering department, Chinma Hegde, and a former student of mine, John Hare, who's been an active part of this collaboration even after having been a student. And then I worked with many students over the years on this project, including Chad, who's in attendance here. And I've even run REU projects over several summers involving undergraduate students working on questions related to the Kaczmarz algorithm. So this has been a rather substantial undertaking, and it's been a source of many interesting questions, lots of interesting conversations, and again, just an absolutely fascinating subject for me. All right, so it turns out that I'll tell you what the Kaczmarz algorithm here is in a few minutes, but I want to illustrate to you throughout the talk that the Kaczmarz algorithm actually brings together a lot of different ideas across a large body of work from 20th century mathematics and now 21st century mathematics, for that matter. And some of it is obvious, or what I call overt, so overt instantiations of the Kaczmarz algorithm. And you see on screen here a list of 3 instances that I mentioned. So linear solver, it was introduced by Stefan Kaczmarz in 1937 as a way of solving a system of linear equations. Obviously a very standard objective in mathematics, and there are lots of ways of solving systems of linear equations, and the Kaczmarz algorithm is one of them. And we've investigated in recent years how we can use the Kaczmarz algorithm to solve systems of linear equations in a distributed environment. So I'll talk a little bit about that here momentarily. And then we can think of it in more general terms as a reconstruction method from measurements. So these are all, as we'll see throughout, hopefully we'll see throughout the talk, these are going to be overt examples of the Kaczmarz algorithm. Then we have what I call incognito instantiations of the Kaczmarz algorithm. So here are some areas where the Kaczmarz algorithm is either a fundamental part or an underlying idea that maybe isn't even so clear that it contributes to the development of the results, but it turns out it's a thread that weaves through a lot of different areas of analysis in 20th century mathematics. So it turns out that the main motivation that brought me to the Kaczmarz algorithm is trying to answer a question about Fourier series. And I'll explicitly say what I mean by that here in a moment. But it turns out that I was interested in thinking about Fourier series, and the Kaczmarz algorithm is actually what makes it work. It was the one that it was the technique that solved the problem for me and for my collaborators. Spectral data. So what I mean by that is reference to the spectral theory of the backward shift operator on the Hardy space. So there's a very rich body of literature on the backward shift operator on the Hardy space, and the reason why it's so rich is because the backward shift on the Hardy space is a co-isometry, so it's not normal. So you can't use the classic spectral theory to study the backward shift operator and its invariant subspaces. But through a large amount of effort across many very talented mathematicians throughout the 20th century, we now have a very strong, maybe even complete picture of what the spectral theory of the backward shift is on the Hardy space. And it turns out that a lot of the analysis, they didn't use this explicitly, but a lot of the analysis actually has behind the scenes the Kaczmarz algorithm. And that really blew my mind when I realized that the Kaczmarz algorithm was in fact in disguise behind a lot of the analysis. Another way that we'll see that it appears a little bit less than overt is reconstruction method, but not from linear measurements, but actually from observables. And I'll tell you what I mean by that when we get to that point. And then I'll conclude our tour through the Kaczmarz algorithm and its instantiations by looking at Fourier series in the multivariable case. So more on that towards the end of the talk. So that's my hope, is to convey to you the remarkable aspects of the Kaczmarz algorithm and the ways that it has appeared in a lot of mathematics in the 20th century and now the 21st century. All right, so here's the part with audience participation. So we just have a system of linear equations, and let's assume for the moment that this is a consistent system of linear equations. So I give this talk to departments at colloquium, seminars. I give it to talks with graduate students. I give it to talks with undergraduate students. So this is always a good way to get participation from the audience, because even undergraduate students learn and know about how to solve systems of linear equations. So what's your favorite method for solving a system of linear equation? If you want to type in the chat box, that'd be great. If you want to share on video, that would be great too. There's a lot of them. So we got a couple of entries in the chat. Anything but Gaussian elimination. Linear programming, yep. Type a command into MATLAB. Yes, I like that. But that would be Gaussian elimination, as I understand it, right? Matrix factorization. Ask ChatGPT. I will admit some of these are not ones I've seen before. Like the last time I gave this talk and asked for Ask for audience participation. I did not get Ask ChatGPT as a response. That's a new one. MATLAB does QR. Okay, so it's doing matrix factorization. All right, so of course, what we teach initially is Gaussian elimination. We teach in linear algebra, when we get that far as a sophistication, we talk about matrix inversion. I'm surprised nobody mentioned any form of matrix inversion. I had one time I gave this talk, somebody mentioned gradient descent, which I thought was fantastic. I actually appreciated that response because it turns out, and I can talk about this a little bit later, it turns out that you can think of Kaczmar's algorithm as a gradient descent method. So it's actually right here in maybe not an obvious way, but even gradient descent for solving a system of linear equations can be cast in a form that looks like the Kaczmar's algorithm. All right, so I'm going to rewrite the system of equations. So I want to think about these as dot products because that'll make a transition to later material easier. So I have these dot products, and so I know the vectors a1 through am, and I know the dot products y1 through ym. And so I'm trying to reconstruct the vector x from these dot products. And so how can we do that? Well, I think many of us are familiar with orthonormal bases, Riesz bases, frames. These are very commonly studied methods for solving, for reconstructing an unknown vector from dot products. We're going to do that differently here. So what we do is we define a sequence of approximations. So we start with some sort of initialization. Often we might choose A0 to be 0. And so that would make the initial estimate x0 to be the 0 vector. That's a perfectly reasonable place to start. And then we construct a sequence of approximations through the Kaczmarz update. So I see a chat came up. Is that something that I should look at here?
No.
Okay. So we do this Kaczmarz update, and if you look at this carefully here, I should mention that I'm assuming for the moment that the A's are all normalized, so I don't have to be constantly dividing by the norm of A. So all the names are normalized already. And if you look at this update carefully for xn as a next update or next estimate from x sub n minus 1, you'll see that there's a projection here. In this case, if you think about x dot a sub n as being a number, which is in this case y sub n, if you think about that as just that number, it turns out this is an affine projection. So what we're actually doing is we're taking the estimate x sub n minus 1, and we're hitting it with an affine projection onto the space defined by the nth equation. Now, if we start with a finite system of linear equations, obviously I'm going to exhaust the equations before I get very far. So what I do is I periodize, I construct an infinite sequence by taking the finite sequence and simply periodizing, so I get an infinite sequence of equations. And so I can construct this infinite sequence of approximations. And if this infinite sequence of approximations converges to what I want it to converge to, which is x, the unknown vector x, then we will say that the sequence is effective. Okay, so I'm still assuming for the moment that the system of equations is consistent, so that there is a solution, there is an unknown x that solves these equations, and this is what I do, or this is what Stefan Kaczmarz does.
Sorry, in the second the update equation with the xn equals xn minus 1,
Yes.
there's a term that's just x.
Yes.
How are you able to do that because you're trying to solve for x?
Yeah, so x dot a sub n is the y's. that I have.
Okay.
Yes. Yeah. So I wrote it in this form to illustrate that it's a projection, but usually you would write y sub n minus x sub n minus 1 dot an times an. Yeah.
Okay, thanks.
So it's a trade-off, but I like to write it this way because I think of things in terms of operators rather than equations. Yeah, thank you for the question. So this is the picture that I have in mind, and I think is very illustrative. So each equation defines a hyperplane in whatever ambient space we're in. We're in finite dimensions. We have a finite set of equations. And we're calculating with the update the affine projection of the current estimate onto the affine subspace determined by the nth hyperplane. So you can see on the screen that if you do this successively, you're going to have this spiraling effect towards the middle here. And since we're assuming for the moment that the system of equations is in fact consistent, there is an intersection to all these hyperplanes. And that's where we want to be. We want to find something in that intersection of all of those hyperplanes. Now, if the solution is not unique, then we can say a little bit more about that. But let's just imagine this picture as being illustrative. And in fact, there's lots to say just about this picture that really emphasizes what's going on with the Kaczmarz algorithm. So the first thing that you'll notice is that every time you do an update, you never move farther away from where you want to end up than you are already at. You can only move closer or not move at all. So that's not a proof that this is going to work, but it's like 90% of the proof that this is going to work, because you never move farther away than where you're currently at. For the formal proof, you need to be more careful. And so what you want to do is you want to prove that the spiraling actually does in fact occur. And so the analysis goes as follows. You cycle through all of the equations once, and then you prove in finite dimensions using a compactness argument that you are in fact closer to the solution than where you started. And there's a constant that gives you how much closer you are. You don't necessarily know what the value of the constant is, but you know it exists. And so every time you cycle through the equations another time, you move that much closer to the solution. And so after cycling through the system of equations once, and then twice, and then three times, you have a geometric reduction in the error term that converges to zero. So that is, in essence, the proof in the simplest case, where you have a consistent system with a unique solution. And that is essentially what the Kaczmarz proof was using this type of idea. And I think that's just a beautiful way of thinking about this. It's one of the earliest examples of alternating projections. So alternating projections is a theme that occurs in many parts of mathematics. In particular, that one that probably is familiar to this audience is phase retrieval. So some of the earliest forms of phase retrieval used alternating projections to do the reconstruction. And there's lots of other instances where that happens as well. So on its surface, it's a very elementary, and I think, dare I say, beautiful method. And the reason why it works, I think, is beautiful, because it's geometric in nature. So one of the things that you can think about just from looking at this picture is, well, why would I project onto H1, H2, H3, H4? What if I project onto H1 first and then H3 next? Wouldn't that be better? And the answer is yes, it would be better, just by looking at the picture. if H1 and H3 are in fact orthogonal, then you would actually get to the solution in 2 steps. But if you're thinking about this in the context of a very large system of equations, you probably don't want to take the time and energy to try to find that type of relationship with the equations. That would be expensive computationally. So one of the variations that exists and was introduced 20 years ago or so is on the Kaczmarz algorithm is the randomized version. This was introduced by Stromer and Verschinen. And so what you do is, instead of cycling through the equations in whatever order they're given, what you do is you pick the next equation at random according to some probability distribution on the system of equations. And what that does is it allows you to capture more of the geometry of the hyperplanes that are determined by the equations. And some of the times you'll pick right in such a way that you'll end up much closer to the solution than if you just simply picked the equations in an arbitrary but given order. So the randomized Kaczmarz has been an object of a large amount of study in the 21st century, and I've looked at that myself. And there's thoughts about what are the optimal ordering. I mean, you can ask those questions. Those are very difficult questions to answer, but people have thought about it. What about non-unique solution or no solution? So let's say a few words about that, because those are natural questions that we always have to account for the situation that the solution either is non-unique or doesn't exist. So in the case of non-unique solutions, there are solutions, but they're non-unique. What happens in this case is you still have the same convergence analysis, and the method converges, but it converges to a particular solution. It converges to the solution of smallest norm or smallest energy. So if you look at this the set of all solutions to your system of equations, that also forms what some people call a linear manifold, or it's a subspace that's shifted away from the origin. The point in that linear manifold that's closest to the origin, this method will converge to that solution. So it gives you not only a solution, but it gives you a solution that you can actually interpret in terms of its properties. And then if you look at the situation where you don't have a solution, so that means that there's no intersection, right? So you can't make the same argument if there's no intersection of all of these hyperplanes. So here what one does is introduce a relaxation parameter. So in the update equation, it's often omega is often the letter that's used. You add an omega there in front of the affine projection, and that value has to be between 0 and 2. And all that does is it changes how far one steps towards the next hyperplane. So in the picture, you have this estimate that's not on any of the hyperplanes. You project onto one of the hyperplanes. So with a step size of 1, or relaxation parameter of 1, you step exactly onto the hyperplane. If you pick a value between 1 and 2, what you do is you actually go beyond the hyperplane into sort of like a mirror reflection. And if you picked a step size, or sorry, a relaxation parameter of 2, what you would do is you would simply reflect exactly across the hyperplane. In that case, you would not end up closer to the solution than where you started, and so 2 is not a good choice because you'll not get anywhere. But if you're between 0 and 2, so if you pick 0, you're not going to move anywhere. If you pick 2, you're going to reflect exactly opposite of the hyperplane. So if you pick between 0 and 2, then you move closer to the solution on either side of the hyperplane. And so you introduce this relaxation parameter, and you prove that the method converges to something. independent of the relaxation. Dependent on the relaxation parameter. So it converges to something. What that something is depends on the relaxation parameter. And then you take the limit as the relaxation parameter goes to 0, and out pops a weighted least square solution. So from a numerical perspective, this is impossible to do because you have to take a limit on the relaxation parameter going to 0. But in principle, we have a convergence analysis for a fixed relaxation parameter and then letting the relaxation parameter go to 0. So the point is we can handle inconsistent systems of equations as well. All right, so there is a lot going on here. I've just encapsulated 50 or 60 years of study, thousands of papers on the Kaczmarz algorithm just in a few minutes. And I've, of course, haven't really said anything about the authors that contributed to all of this. But I'll pause there and say we could talk about this for a very long time. Just thinking about this picture and the variations of the algorithm that this picture prompts. So one thing that I do need to mention, two things that will be important for us a little bit later. One is that for the estimate x sub n, so wherever you are in your sequence of equations and you're at the nth sequence and you've calculated the nth approximation, that element x, or that element of the space x sub n is actually in the span of the A1 up to the AN. So you're always within the span of the vectors that you've used to calculate the approximation up to that point. And while this is formulated as an affine projection, if you basically move the center, which is the intersection here, to x, so that becomes the origin. So the intersection of these hyperplanes is the origin. Then this becomes all linear projections, and the nth approximation is actually a linear operator acting on x. And so you can formulate this through linear operators, and those linear operators actually are constructed through another sequence of vectors that when I've written my papers, I've called them G1, G2 up to Gn and then off to infinity. And it looks like a frame, approximation where x sub n is the sum of the inner products of x with g sub k times a sub k. And that auxiliary, so that other sequence of g's, that auxiliary sequence is going to play a little bit of a role in our conversation later. And it turns out that sequence, that auxiliary sequence, comes from a giant matrix inversion. So we're solving the system of linear equations through this sequence of projections. When you do the convergence analysis, it turns out that in the background there is this giant matrix inversion, not the original matrix though. You take the Graham matrix of the A's. So in this case, if we periodize, so we have an infinite sequence of A's, you look at the Graham matrix of that, you look at the lower half of that Graham matrix, so the lower triangular part, with ones along the diagonal because the A's I've normalized. So that lower triangular matrix is, in principle, algebraically invertible because you have non-zero entries along the diagonal. It's an infinite by infinite matrix. But what we can do is we can calculate an algebraic inverse of that lower triangular matrix. And that is what gives rise to the auxiliary sequence, and it gives rise to some of these other things that occur in these other incognito instantiations of the Kaczmarz algorithm. Okay, so let me go through this part quickly. I've been thinking since I've been interested in the Kaczmarz algorithm. Initially, I've been thinking about, in the realm of data science, in the era of data science, how do we want to leverage the Kaczmarz algorithm? Well, one of the things that we sometimes do is we try to solve a system of equations in a distributed environment, meaning you have nodes on a network, so you can imagine, servers on a computer network, or you could imagine, say, a swarm of drones that are trying to interact with each other. And you have a system of equations where some of the equations are scattered across the different nodes on the network. How might we solve the system of equations without aggregating all of the equations in the same place? Let's say you either can't or don't want to do that for one reason or another. So one of the things that we looked at is a distributed form of the Kaczmarz algorithm. So this graph here imagines that at each node of the graph, you have a single equation. We construct a spanning tree of the graph. And so we have a root node and then all the remainder nodes. And what we do is at each node, we do the Kaczmarz update with the single equation that that node has. Then that node passes that estimate to its downstream neighbor in the spanning tree until that propagates to the leaves of this tree. So what's interesting is now we're going to have multiple estimates, one for each leaf in this graph. And what are we going to do with all of those estimates? What we're going to do is we're going to back propagate, and that's a loaded word in the era of machine learning, but we're going to back propagate these estimates back to the root and simply take some sort of combination, like a convex combination of those multiple estimates back to the root node. So going from the root to the leaf, the estimate is based on only some of the equations, and that's true for every leaf. So nothing sees all of the equations simultaneously. But then when we back propagate to the root, then the root node actually has estimates that in aggregate has seen all of the equations. And we prove convergence analysis of both consistent and inconsistent systems of equations under this iterative process of propagating forward from root to leaf, back propagating from leaf back to root, and repeating that cycle. And I'll mention that here's where one of my projects with RU students came in. We were looking at how to accelerate the convergence in this situation. And one of the things that they found, which was absolutely fascinating, is you can utilize a relaxation parameter in the case of the distributed Kaczmarz, where the relaxation parameter was bigger than 2. So if you remember in the classical case, if you pick a relaxation parameter bigger than 2, you're going to end up farther away than where you started on the Kaczmarz update, and you will not converge to where you want to converge to. In the distributed case, because you're distributing errors across multiple estimates, if you can actually pick a relaxation parameter greater than 2, speed up the convergence, and still have convergence to what you want it to converge to. And that was a fun project with our RU students, where they realized that they could go beyond this seemingly hard threshold of 2 with a relaxation parameter. Okay, what about linear measurement? So now I'm going to transition momentarily to thinking about infinite dimensional spaces. So I want to think about an infinite dimensional Hilbert space H. Suppose I have a sequence of unit vectors, and I ask the same question: how do I recover X from, I wrote it in the form of a dot product, but suppose I want to reconstruct from the sequence of inner products. Well, again, for this audience, many of us are familiar with, of course, orthonormal bases. If the A's are an orthonormal basis, we know exactly how to do it. If it's a Rees basis, we know how to do it. If it's a frame, we know how to do it. What if it's none of those things? Well, it turns out that there's a lot that can be said with respect to the Kaczmarz algorithm in the case of an infinite sequence in an infinite dimensional space, but very little of it is something that we can really get our hands on. So for example, if the sequence is an orthonormal basis to start with. Of course, we can do the reconstruction immediately because we know how to reconstruct with an orthonormal basis. But we can actually use the Kaczmarz algorithm to do the reconstruction on the sequence. And if it's an orthonormal basis, it will work. If the sequence is a Riesz basis that is not an orthonormal basis, then it will not work. It can't work. And that's a result by Wojtek Chaya and one of his collaborators, that a Riesz basis that is not an orthonormal basis will fail when using the Kaczmarz algorithm. And I bring that up because what that says is that in frame theory, we look at perturbations, like frames are stable under small perturbations. And what that says is that sequences for which the Kaczmarz algorithm works, so effective sequences for which the Kaczmarz algorithm work is not robust to small perturbations. Any arbitrarily small perturbation can destroy the effectivity of the sequence. And so many of our usual tricks to try to understand collections of sequences like frames, in this case, a collection of sequences that we want to know whether the Kaczmarz algorithm works, does not admit that type of perturbation analysis. Now, it turns out that there's a complete characterization, but what you have to do is you have to go back to that giant matrix inversion that I mentioned before. So you calculate the inverse of that giant half-gram matrix, and then you have to test whether that matrix satisfies a certain condition. And of course, numerically, that's not possible because you have to calculate this infinite by infinite matrix. You have to invert that infinite by infinite matrix, and then you have to test the condition. So it is a complete characterization, but it is not, unfortunately not very useful for the types of things that we want to do. Okay, but there is one result that actually is we found very useful for us. And that is if we have an infinite sequence of vectors in an infinite dimensional space, which is stationary. So what does stationary mean? Well, it means that if you take the inner product of any two vectors, so phi sub n and phi sub m, and then you increment the indices by the same amount. So you shift in the sequence by the same amount. So phi sub n plus k, phi sub m plus k, that inner product is the same as what you started with before you shifted. So if the sequence has that property, then it's called stationary. And if it's stationary, that means, to go back to something I learned from Larry Baggett, you have Bachner's theorem, you have a representing spectral measure coming from Bachner's theorem because this gives rise to a positive function on the group of integers. And so there's this spectral measure behind the scenes when you have a stationary sequence. And what you do is you look at whether that spectral measure is either Lebesgue measure or it's purely singular. So one of those two extremes. And if it's one of those two extremes, then the stationary sequence actually is effective. And this is proof by Kvapian and Michalski 25 years ago now. And it turns out this singular condition is what makes what I was ultimately interested in initially. It makes this work. So for us, the focus is going to be on the purely singular part of this. So we have one nice proof that says under this condition, the sequence is effective. Okay, so here is the original motivating question that I was thinking about when I first encountered the Kaczmarz algorithm. So suppose we have a measure nu. Let's suppose that for convenience, it's supported on the unit interval 0, 1 on the real line, so one dimension, and is supported on the unit interval. Is it possible to take any function in the L2 space with respect to that measure and write it as a Fourier series expansion? This is the question that I was motivated by. So to emphasize the context of this question, if you take the measure nu to be Lebesgue measure on the unit interval 0, 1, then the answer is yes. You can. We learned this in elementary Fourier analysis, that you can express any function that's square integrable on the unit interval. as a Fourier series with respect to the exponentials. And the reason why is because the exponentials are an orthonormal basis. That's what you ultimately prove in either real analysis, harmonic analysis, one of those standard graduate level courses. But if you replace Lebesgue measure with any other measure whatsoever, assume it's Borel for well-defined purposes, but if you replace it with any other measure, you immediately lose orthogonality of the exponentials. And if there's any singular component to this measure, you lose any hope of frames, at least using the integer exponentials. So I want to emphasize here that in the lead up to this was a question that's still open regarding the middle third Cantor set. So we have a world-renowned expert here in Palle Jorgensen in the audience who introduced us to spectral measures. So these are measures that have a sequence of exponentials that form an orthonormal basis for its L2 space. And they have very nice constructions that have led to many other dozens and hundreds of constructions for spectral measures. And their canonical example is what we call the middle fourth Cantor set. So you take the unit interval, you divide into fourths, and then you keep the first and third, and you discard the second and fourth subintervals, and you repeat. And it turns out there's an invariant measure for that process. That invariant measure is spectral. And so there's a sequence of exponentials with frequencies that are irregularly spaced, but sequence of exponentials that form an orthonormal basis. Now take the middle third Cantor set, which we're more familiar with, where you simply remove the middle third every time you do the updated approximation. That has an invariant measure. That measure does not have an orthonormal basis of exponentials, so that was a proof in Palle's original paper. So an obvious question for those of us coming from a frame theory background is whether there is a frame of exponentials. And that problem is still open. It's still unknown whether the middle third Cantor set has a frame of exponentials. Now, if the answer to that question is yes, then if we have a frame of exponentials, then we know how to expand vectors in that L2 space as a series expansion with respect to those exponentials using frame theory. And so we would have a positive answer to this question. But since we don't know whether the middle third Cantor set has a frame of exponentials, is there anything else we can do? And the answer is yes, we can use the Kaczmarz algorithm. So if we have any singular measure, then the exponentials with respect to that singular measure is a stationary sequence. The spectral measure is the original measure itself, the measure nu. And so if we assume a priori that it's singular, then we know that the Kaczmarz algorithm actually works using the exponential functions. So we look more carefully at the sequence of approximations. That's where the auxiliary sequence comes in. And we look carefully at that, and we get that every function in the L2 space, when the measure is purely singular, it can be expressed as a Fourier series expansion. And I want to emphasize with just the non-negative frequencies. So it turns out that a result due to the Riesz brothers is that when the measure is singular, the exponentials with non-negative frequencies is actually a complete sequence in the space, in the L2 space. So we only need the non-negative frequencies to do this Fourier expansion. So this comes precisely from the Kaczmarz algorithm. Now you asked the question in the way I formulated it, which was the motivation that we first had, and it doesn't look like the Kaczmarz algorithm is going to help us at all. And yet it turns out it's exactly the right tool that we needed with the Kłapian-Michalski theorem to be able to answer this question. Now, it turns out that there's a lot to the story here regarding simply trying to answer the question of, does there exist Fourier series expansions for this L2 space? And the reason why is because when you have a singular measure, it turns out through the Herglotz representation, there is an inner function associated to it, which gives rise to a model space for the backward shift invariant, the backward shift. So model space is an invariant subspace under the backward shift. There's something called the normalized Cauchy transform. There's the spectral theory developed by Clark in the 1970s, and that has been extended in various ways since then. So there are a lot of pieces floating around here when we simply start with an L2 of a singular measure that all of a sudden pop into place because of all of this existing work that originates with the Hergelotz representation from the early 20th century. And if you look carefully at all of the interconnections between these constructs, the normalized Cauchy transform, the model subspace versus the L2 space, the relationship between them, so this gets actually to some complex analysis where we're looking at boundary representations of a subspace of a Hardy space. It all is encoded. Now, this is not the way that any of these people were proving these things, but it's all actually encoded through the auxiliary sequence of the Kaczmarz algorithm. So you can actually reprove many of these connections, many of these constructs, and we do extend these ideas using the auxiliary sequence from the Kaczmarz algorithm. So it turns out that the spectral data for the backward shift on the Hardy space of the unit disk, it's almost entirely encoded within the auxiliary sequence of the Kaczmarz algorithm. So it turns out that it's there. It's not obvious that it's there. It certainly was not utilized in terms of developing the theory, but it actually is a thread that ties all of these things together. And so as my former PhD student, John Hare, and I, and together with Pale and then Chad, as we were fleshing all of this out, it just is really remarkable to me to think about how all of these things are tied together through something that was designed initially to solve systems of linear equations. So that's one of the many remarkable things that I've been fascinated by over the last 10 years. All right, now here's another question that gets a little bit into the weeds. If somebody wants to hear more about Paley-Wiener spaces, I can come back to that, but in the interest of time, I'm going to skip over this for now. So we've talked about how to do reconstruction with linear measurements or inner products. What about if our data is coming from operators instead of linear functional? So if you take a vector and you hit it with a sequence of operators, can you reconstruct from that? And some of you may have some familiarity with fusion frames. So this was very popular from our friend Pete Kazaza, who was very interested in fusion frames, and many others that he worked with. Fusion frames, you have this idea that you do some reconstruction locally, and then you try to piece together the local reconstructions. And it turns out that one way to conceptualize that is through this view of hitting a vector with a sequence of operators. And can you reconstruct from those images? And the answer is yes. You have to make certain assumptions about the operators to even make this sequence of updates well defined. But make those assumptions, and then will this give you the solution that you're looking for? Will it find the unknown x vector x? Well, it turns out if you can prove that the sequence of operators is effective, then the answer is yes. And that is a very subtle question, because the way that we would normally do this analysis is you would look at that Graham matrix, the inner products of the original vectors A, and you look at that inversion, test that condition. Well, now we have operators. So now we have to generate these infinite by infinite matrices whose entries are operators and mimic this same process. And we can do that. It turns out that you can pass through this, and we were able to make that successful. But it isn't an immediate or trivial extension. But you can do this in principle. And we were able to use this to extend our results of Fourier series from functions of a single variable to functions of several variables. So in this case, I just wrote this on screen as thinking about 2 dimensions. So suppose we have a measure nu that, let's suppose it's supported on the unit square in the plane, and we look at the integer exponentials in the 2 variables. Can we express the function as a Fourier series expansion? So again, to think about the example when the measure on the unit square is the Lebesgue measure, the answer is yes, again, because of orthogonality. So if you replace that measure with any other measure, you lose orthogonality. And most likely you're going to lose any hope for frame expansion. So we asked how to expand this result from 1 variable to 2 variables. And it turns out that we had to make a bit stronger of an assumption on the measure nu. So we have something that we call slice singular. So this is work with Pale and Chad and John introducing this idea of slice singular. So what you see on the screen is you see examples, 2 in 2 dimensions and 1 in 3 dimensions, of measures that meet our definition of slice singular. And these are fractals. They're generated by iterated function systems, iterated function systems that are affine contractions. So these aren't the only fractals that people study, but these are the types of fractals that we like to study. And it turns out that fractals that are generated this way do satisfy our slice singular condition. So slice singular is a strictly stronger condition than singular. So in 2 variables, 2 dimensions, every measure that is slice singular, according to our definition, is singular, but not vice versa. So we have examples of measures that are singular but not slice singular. So that does limit the scope of our results, but for our purposes that we really like to study these fractals, this works. So slice singular, what one does is, so this is where things sort of get off into the weeds. We look at disintegration of the measure into a marginal measure and what we call slice measures, or you can think of those as conditional measures. And what we need each of the slice measures to be singular as 1-dimensional measures, and we need the marginal measure to also be singular as a 1-dimensional measure. And if we have all of those conditions in place, then the answer to our question is yes, we have the conditions that we need to express this function as a Fourier series expansion. Now, I'll mention 2 things explicitly here. One is the way we do this is through this operator value Kaczmarz algorithm. So we actually use a sequence of operators on our space that we hit F with, and then we go through the full methodology of the Kaczmarz algorithm, the analysis, the convergence analysis. It turns out that there's connections here with the Branch spaces, which that has its own long, very interesting story that I'm absolutely fascinated by. We use direct integral decompositions of operators to get the conditions that we need for convergence. The second thing I'll mention is that this convergence is very subtle. First of all, it's conditional. So we cannot switch the order and then just simply sum. We must sum in the order in which we do the decomposition. And even for each individual sum, it's a conditional convergence. And so that is subject to, you can't reorder. If you perturb the coefficients by a small amount, you can destroy convergence. So this is a very brittle convergence, but it still does converge to the unknown function. Now, in terms of switching the order of the sum, you can switch the order of the decomposition of the measure which switches the order of whether you sum in the x variable first and the y variable second, or vice versa. But what you actually have to do is you have to recalculate the coefficients. So it turns out if you want to switch the order of the sum, the coefficients that work are different in the other order from the original order. So I'm not sure I have a full understanding of why that is, but it comes from the way that you do the decomposition, the disintegration of the measure. And so because those parameters can look very different depending on the orientation of the disintegration, that's why the coefficients ultimately end up being different. Okay, so I've got just a couple minutes left. I could tell more of the story of the 20th century mathematics that sees the Kaczmarz algorithm as a thread through it. So here are just many of the words that I mentioned earlier in the discussion, and I can say more about that if there is interest. But maybe I'll stop here, come back to our final slide in 2 dimensions, and open the floor up to questions.
Yeah, let's see. Before questions, let's thank Eric for his talk by clicking buttons.
Yes, thank you very much.
There they are.